rough here in a second. So Chris, just a brief kind of outline, background on Chris. Chris got his bachelor's, his master's, and his Ph.D. at the University of Guelph, which is in Canada, for those of you who don't know, north of Toronto. And Chris has been at York University since 2012, where he's worked up the ranks to associate professor now. Over his brief but ever-growing research career, he's accumulated over $1.5 million of funding, the vast majority of that being extramural funding. He's not only a great scientist, but he recently received the Dean's Award for Excellence in Service, and so he wears many hats and wears them well, although maybe custom fitted for his larger than average head.
Oh, there we go. I was like, something's coming up here. You grow the tree and you knock it down.
So he's mentored and graduated 4 PhD students already in his 7 years at York, and that's pretty impressive given that the time frame of pushing a PhD student through takes a while on its own. He's given over 40 invited lectures, not including this one, over 40 invited lectures in 10 different countries. And so he has 47 primary research papers. 7 of those are senior author, but it's important to note that 6 of those senior author papers came just this last year. So, if you want to look for a trajectory, I think it's pretty clear that Chris is on his way up. But outside of all the research, I just want to take a minute to talk about how amazing this guy is. And so in August of 2008, a very clueless, naive Dan Lark went to East Carolina University to start my master's program. And the same week that I started, Chris was starting his postdoc in the same lab. And since then, Chris has been by far the most instrumental mentor I've had in my life. So he has guided me at every step and looked out for me. He's a good man, and he eats a lot of ribs. Sometimes I make them. But it's just amazing to have him here. It's a personal just joy. And so please help me in thanking Dr. Chris Perry for coming and giving this presentation today.
Now I have to be nice to you. Okay, where's the Kleenex? There's actually a Kleenex here. That's incredible. Oh my gosh, thank you. You can't, oh. Look at this. Which one's water? Everything you expect me to say right now, you can predict. And I hope it doesn't sound cliche. There's more to a career, I think, than just what you do. And it's all of this. It's people for sure. I'm very lucky where I work. I have great people, and this has just blown me away. I can't thank you enough for all being here. And the program that was set up, the itinerary, the can bringing me in. Barry, thank you for having me here. You know, it's often a fly-in, a really good, productive day of meeting people. You give a talk, and then you're out the next day. I've been here already since Wednesday, and I'm leaving tomorrow. Normally, the audience, I'd say, oh, I met 3 or 4 people already. There's 3 or 4 people here I haven't. I actually feel I've seen all your faces already. The program has been outstanding, and thank you for setting this up. You guys are all lucky to work here, honestly. You've made me feel very well. Thank you. Talking with students today, the diversity of thesis topics, what was going on was so interesting. And I'm sorry I talked so long to each of you. I know there was an hour for you to talk to me, and I think I stopped asking you questions at it was at 12:45. It was so interesting. You're all doing great work, honestly. Such a great place. And faculty as well, as I mentioned, I've got to meet people that I've known the names for so long, and even emailed some people over the years. Lastly, Barry was my external examiner for my PhD in 2008, and we've kept in touch, email and so on. And then I saw him yesterday, and you know, I felt like, oh yeah, I've seen Barry around. I actually don't think I've seen Barry in 11 years, but it felt like it did. And boy, are you lucky to have him at the helm. So constructive as a student, and a huge impact on me liking what I do. I can't believe this place. So thank you for having me here. I want to come back. Well, I'm done. Anyone want to get a beer? This is what we did. Any questions? Okay, 308. I should have deleted that extra slide I added. Most of you heard my path. I have a slide. The next slide is called My Path, because normally I've learned over the years giving talks, it's really great to tell the students up front a little bit about yourself, but I'll skip over it. I didn't train in this at all. Duchenne muscular dystrophy, all the disease models we're looking at now, generally we're a muscle wasting lab. Generally, I say that because we also just published a cancer paper. But we're really interested in how mitochondria dictate cell fate. Why do mitochondria help a cell grow? Sometimes mitochondria kill a cell. When it doesn't kill it, it makes it weaker. And of course, muscle physiology's background. We generally apply that to diseases of muscle cells that are dying. So atrophy models. This is only one of several muscle wasting disorders that really have a huge impact on people with it. But we do apply that same question to, we're trying to stop mitochondria from killing muscle cells, but we're trying to make mitochondria kill other cells like cancer. And if you understand something, whatever you study at a conceptual level, it's really fun to think outside of the disease or condition you're looking at. What else can we apply it to? So we've been doing that. Apply our expertise in mitochondria to a disease I've never studied. My path, skip that. All right. So that was all nice and fun and dandy. I think one of the things that I found motivation in starting as faculty was trying to apply expertise to conditions that have really limited therapy. Okay? Even though I've never studied those conditions before. And I went to a talk once on Duchenne muscular dystrophy and totally fascinated at what is this disease? And you'll see in a minute, it has nothing to do with mitochondria as a cause. But then data evidence emerged that there are secondary metabolic dysfunctions in the disease. And I wonder if that's a secondary reason why muscles might be fatigued. People have been proposing that. And as soon as I heard metabolism, maybe a secondary failure of metabolism in this disease, I wondered what we could do. So I learned about it. This is usually the first symptom of Duchenne that a parent sees. And it's almost always in boys. We're getting to that as soon as genes. But usually, mom and dad see a boy using their hands to stand up. Perfectly happy, but having difficulty. Go to the doctor, do a gene test, and diagnose with Duchenne. In the worst cases, this doesn't happen to everyone, but in the worst cases, you start to see postural abnormalities at 8. And in the worst cases, you can be wheelchair bound at 15. Around this time, respiratory insufficiencies start to happen. And later on in life, usually not this young, you start to develop cardiomyopathies, okay, heart failure. That can lead to heart failure. So it's a skeletal muscle, including diaphragm and heart weakness disorder, really a wasting disorder. I took the slide out, but typically 40% of those that pass away with Duchenne die of respiratory failure, mostly diaphragm problem, and the other, another 40% will die from cardiomyopathy. Okay? And it used to be untreated, lifespan ended in your 20s. Nowadays, we'll talk a bit about the current therapies. All we really have are glucocorticoids, which are potent anti-inflammatories. They do a lot of other things as well. But the immune system is so ramped up with all this dying muscle cells, constantly trying to assist in repair, because inflammation is important for muscle repair. There's too much inflammation. It's actually thought to be contributing to some cell death. So the irony is, well, you need the inflammation for regeneration. They actually shut down your immune system with prednisone, so glucocorticoids. And that has extended lifespan to 30s and 40s. Big breakthrough. That's the only real therapy we have. And it's still not good enough. So, before we get into what we can do about it, what is this disease? Essentially, when you have muscle wasting progressing over the years, you actually can often see limb diameter getting bigger. It's strange to see someone with atrophy actually looking bigger. It's because it's being replaced with fat and fibrotic tissue, particularly in the limbs. And obviously, the decrease in functional muscle results in muscle weakness. I already said this, I thought I did this slide. So you live with a need for assistive devices in mobility. You live with a need for respiratory assistance, in severe cases, a ventilator. And you very often are on a series of cardiomodulatory drugs. It's not uncommon to be on beta blockers and some other things, all sorts of things, depending on what sort of cardiovascular problems are arising from cardiomyopathy. Now, thankfully you have sight to these. What is the disease? It's a mutation in the gene called dystrophin. And dystrophin is one of the longest human protein coding genes. It's got 79 exons, over 2 million base pairs. And let's just call that a lot of opportunity for point mutations. In fact, there's no single point mutation in muscular dystrophy. There's dozens of known point mutations that lead to that same symptom you saw. That are ultimately linked to a lack of functional dystrophy. It's X-linked, so it's almost entirely in males, incredibly rare in females. You know, for a female to have it, both your mom and your dad have to be carrying. So very, very rare in a female. And it's varying severities because it depends where the point mutation is, which determines what the length of the protein is and how much it can actually still function. There are emerging genetic therapies, okay? If we're ever going to cure the disease, we have to restore the normal coding. But that's a common problem for all diseases, or for many diseases, right? And we're a long way away from that happening, but there are promising results coming out in preclinical models. Some of them are making it to clinical therapies. Certainly not gene rewiring the code per se, but exon skipping, skip the exon. Live with a shorter protein. There are promises emerging. There's certainly no cure. We reason, until that day comes, if all we're doing right now is targeting a secondary complication of disease, inflammation, could we identify another secondary complication and then target that? Now, why would we ever question mitochondria in your dystrophy? Well, what is dystrophy? Here's the extracellular matrix. Here's the sarcolemma, the cell membrane of the muscle. And here's the cytoplasm. Cell membranes adhere to the extracellular matrix, where all the collagen is, and so on, through laminin and through a dystrophyte complex. Dystrophin, right here, is part of the cell adhesion apparatus. But it's on the inside, and it actually connects the cytoskeleton to the cell membrane. So an analogy I used earlier is think, the walls here are the cell membrane, but how are they being held up? Through wood, through steel girders, through posts. Well, that's your cytoskeleton. Posts in the wall of the cytoskeleton. But how are the posts connected to the wall? How is your cytoskeleton connected to the cell membrane? Through an anchor, dystrophin. Posts are all bolted in. So dystrophin is like the bolt. So imagine you move all the bolts. It's there, everything's holding just fine. But what if you push it? What if you put a strain in the wall? What if the wind comes? So imagine not having that bolt. Imagine not connecting your cytoskeleton to the cell membrane. You have a very disorganized cytoskeleton. This is going to lead to atrophy through a myriad of ways, all sorts of cell type. But from a functional perspective, we have a problem. We actually have a very unstable membrane as well. See, the cytoskeleton hooking up is really holding the membrane together. So what happens under intense contractions, probably not mild, to be honest, is you put a lot of shear stress on the cell membrane on an intense contraction. Say you're running upstairs or something, your fibers rip. Much more than us, much more than if you have dystrophy intact. It's a disease of an unstable membrane. Well, this is super intriguing from a pathophysiological perspective, because why do we even need cell membranes? Imagine now having a very flexible cell membrane, one that's carrying these things. We lose the very purpose we have one, which is to compartmentalize everything, particularly ions, calcium, all sorts of salts, substrate uptake, managing glucose uptake, insulin signaling, anything membrane mediated is compromised if you can't maintain an intact cell membrane. This is starting to build to why mitochondria would ever be relevant to dystrophy. We don't know, spoiler alert, mitochondrial dysfunction, but we don't know why. The theory is likely calcium stress. We keep a lot of calcium outside the cell, not too much inside. It's highly regulated. It's been shown calcium is through the roof in cytoplasm of this dystrophic muscle. And if you put too much calcium in the cell, it gets into mitochondria, makes it swell up. Probably causes dysfunction. But probably all sorts of other reasons why a compromised cytoskeletal cell membrane tethering might lead to all sorts of problems with mitochondria dysfunction. At a whole muscle level, what you see is now, in a healthy person, if you get an injury to your muscle, okay, so you run down a hill, or you lift something too heavy, you tear your muscle, or you get an infection, yeah, the damaged fibers will die. It degenerates, and you regenerate, right? Hurt your muscle, you regenerate. When you lack dystrophin, you become less tolerant to an injury. In fact, what is normally a very normal contraction is now actually an injury. You get cell death, you get massive degeneration, and your muscles try to keep up. Stem cells are turning on, trying to regenerate, but over years and years and years, they're failing. They can't keep up fast enough if the degeneration is occurring, so you get atrophy. Think of a muscle that never gets to stop. The diaphragm. The amount of cell death that's occurring in the diaphragm over years, and how repatriate's occurring, so like, you have to go on a ventilator by your teens or 20s. Your skeletal muscles, you can choose to sit. You can choose, I'm not going to run up the stairs, I'm not going to do something too intense, stuff like that. You can't do that with your heart or your diaphragm. Cause of death, diaphragm failure, heart failure. The only standard of care we have are attenuating massive amounts of inflammation that are constantly ramped up whole body in response to all of this dying muscle. You need inflammation to remodel a damaged cell to allow regeneration to occur. You need that. But imagine it's ramped up too much. It can actually contribute to pro-death signals. In other diseases, it's TNF-alpha and other things. It might be the same here. So you actually want to bring it down a bit. Now, people are living in their 30s and 40s. Cop interview with Dr. Turner-Polsky and his colleague is the only other therapy that was proven in clinical trials to actually improve grip strength in Duchenne patients. And I believe, don't quote me, no, it wasn't. It wasn't, I thought it was 6-week off test. It might be. So Dr. Turner-Polsky, we've been very fortunate to have him 1 hour down the road at McMaster University. He's got the largest neuromuscular disease clinic in Canada. And he's really given insight into the design of our mouse studies. And he gives his patients creatine and prednisolone, and actually he gives all sorts of nutritional supplements as well. There's some evidence to support it, and he gets very good outcomes. But why aren't they living till 70, 80? How do we improve their functional years even better, regardless of lifespan, health span, and lifespan? We don't know what else to target until gene therapy is taken, if we ever do. So with this lack of dystrophin, right, here's your muscle, here's a muscle fiber, here's the dystrophin, you get a weak member, you get tearing. It's thought that you can no longer keep calcium outside the cell and a lack of other things. They come in, they create all sorts of stresses. One stress that people assume is the cause of mitochondrial dysfunction is mitochondrial calcium stress overloading the mitochondria. There's also evidence of increased oxidative stress over years. Megan Hughes, who was seeing the data, she started her Ph.D. And we looked in the literature to see what the evidence was for where the oxidative stress was coming from. Where was the ROS coming from? Everybody said it would be mitochondrial because of this calcium overload. When you actually looked at the literature, there was only one reference that actually measured it quite well, mitochondrial ROS, and they actually showed it down in a mouse with muscular Duchenne, dystrophin mutation, not up. But they also saw glutathione and antioxidant capacity was pretty up, so they wondered if it was compensating. But still, there was no evidence that mitochondria was a source of ROS. Some evidence emerged from Chris Ward at Baltimore, University of Maryland, that it's not just mitochondria, there's a cytosolic ROS, NADPH oxidases. Probably lots of sources of ROS. But we wanted to know the role of mitochondrial ROS. When we saw this study that showed this bizarre lower mito-ROS and really high antioxidant capacity, we wondered, what if we reevaluate this question with new approaches? Before I get to that, we also asked a bigger question of why would ROS ever be relevant to muscle function? See, mitochondria can ultimately trigger cell death through two processes. One is apoptosis and one is necrosis. I won't get into the signaling pathways for each, but ultimately two things are common with this. You get an increased cytochrome C release, which triggers apoptotic pathways in particular, and increased H2O2. And you see this in other models of muscle wasting. Diaphragm unloading, work by Scott Powers. Okay, if you go on a ventilator, actually within very quickly you can start to see proteolysis occurring in the diaphragm. It's like a disuse phenomenon. But you see this sort of relationship happen in mitochondrial ROS problem. Ischemia reperfusion, experts in this room know about that. In heart, if you cut the nerve to a muscle, it wastes away. But one of the first events is increased mitochondrial ROS. No one really knows why. But you still see mitochondria can dictate cell fate in these models of muscle wasting. You get this increased H2O2, and one of these two can happen and you get cell death. So we simply asked, well, let's test this speculation everyone's had. In Duchenne, do you get elevated H2O2? And what we're really asking, is this a new therapeutic target? Is this another secondary contribution to disease? Sort of like inflammation. I'm going to skip over this because we've got great mitochondria people here, plus it's only for slide. And I love this slide. I stole it from him. I put a patent name on it. But I'm going to just jump to the end. When you design a mitochondrial protocol to assess mitochondrial respiration, or mitochondrial ROS, you have to think very carefully about your buffers. There's standard buffers, totally validated, standard protocols, all this stuff, and they do give you great insight. But don't hesitate, sort of my soapbox speech to a student, is don't hesitate to think a little bit more about what you can add to the buffer to capture a critical in vivo control parameter that is not present in your buffer. Now, we make ATP when ADP goes up. Exercise, contract, myosin, circuit, everything uses ATP, ADP goes up. ADP stimulates ATP synthase to make ATP by opening ATP synthase, allowing protons back in. It's a concept of memory of potential. Ultimately, by lowering memory of potential, you permit electron flux ultimately from the food through NADH. What's not drawn is FeDH2 complex 2. What I'm saying is your food is stripped down to electrons. Electrons are pumped, are shoveled through the electron transfer chain of oxygen. In this process, you can get some premature electron slip to make H2O2. The point here is when you make ATP, you do make some ROS. But that actually depends on how much ADP you have. And I won't get into it, but a lot of assays for reactive oxygen species don't put ADP in their buffer. They just measure ROS production in response to a challenge. But if you actually add ADP, you change the interrelationship between metabolism and ROS production. And when you do that, you get very different ROS results. And for all we know, maybe Duchenne muscular dystrophy is creating a mitochondrial stress that ADP doesn't work, or something else doesn't work, and it's not in our buffers. Keep that in mind, because what we did was we designed in vitro assays to capture the critical role of ADP. We threw ADP in our buffer even for our assays. I know a lot of that requires much more explanation, but one of the advances we tried to do was not just use a standard buffer, we tried to throw in ADP at multiple concentrations in all assays to see the dysfunctions there. That'll be far more interesting than the sugar glass. So if we're ever going to target mitochondria, we're going to first determine the full degree that it's dysfunctional. So Sophia and Megan did this work. They're just outstanding. They're both defended. So we used a mouse model called D2MDX. For anyone that knows anything about muscular dystrophy models, there's a classic model, the C57 mouse strain. Massive insight gained from these models, but widely recognized to actually be super, super efficient at muscle regeneration, even better than a human. And so people start developing new models that aren't so good at muscle regeneration and actually have worse muscle waste, which many researchers say this model looks more like a human. So we tried to reevaluate that old problem where no one could find mitochondrial loss. We tried to find it in a new model. So first we had to characterize this muscle, and what this is hind limb muscle. So in a mouse, you can stimulate the hind limb and measure force production. Then we compared it in a healthy wild-type mouse versus this dystrophin mutant. And so here we are at a range of frequencies. Here's your force production in the wild-type, and here it is in the muscular dystrophy. We're just validating the model. Okay, well known. The max torque is lower. We collaborated with Dr. Jeremy Simpson at Guelph, who has this really interesting method to indirectly measure respiratory muscle function in the mouse. So how do you measure respiratory muscle strength in a human? Think back to your X-phys labs. It's different things, right? Spirometer. And what do you say to the person? Blow as hard as you can. Blow as fast as you can. So how do you say that to a mouse? How do you get at maximal respiratory function in a mouse? You can't ask it. Well, this might sound terrible, but it's actually safe. You kind of make them do it. So what he did is he puts a very small catheter that's got a pressure transducer. And you can't even measure it in millimeters. It's in French, which is like fraction, like 1.8 French, it's a fraction of a millimeter. Puts it down the esophagus under their sleeve, or their anesthetized. Put a pressure transducer in the stomach. And then pull up just a bit to the esophagus, okay? You're above the diaphragm, but in the esophagus. Now, they're on a breathing tube down the trachea, breathing the anesthetic. But it's also their source of air. Just clamp the hose. And you can see the contractions getting stronger. And what it's doing is the diaphragm is contracting harder and harder and squeezing the stomach and creating esophageal pressure. So this is pressure of inspiratory pressure, PI, during occlusion. And you can get maximal diaphragm contractions of it. No pull past 30 seconds, and that's just totally fine. So it's a stress test. Now it's a negative pressure, because as the diaphragm is contracting, sorry, it's not squeezing, it's pulling down, and it's actually creating a negative suction pressure. So you get this negative suction pressure in the wild-type mouse, really strong diaphragm, and you need to, at 30 seconds, you saw the weakness. That's how you do it in vivo. We really benefit from smart people around us. We validated the model. We've got limb muscle, we've got diaphragm, or respiratory muscle. That could be intercostal as well. Body weight is down. We do three-dimensional micro-CT analysis. We can reconstruct muscle volume in a living mouse with CT scans. Volume is trending down. Voluntary row running, down. Page hang time, I'll go over this in a bit, down. Grip strength, down. How do you measure grip strength in the mouse? We'll go over this. We got the right model. So then we looked at respiration. JO2 is oxygen consumption. Now, remember I said we want to model ADP. A lot of people do this. Don't just add maximal ADP to alpha, which was sort of standard. Why don't you think about what your ADP is? What's your ADP concentration? So you go in the human literature, find it out, add it to the chamber. So it's actually, right now you're all about 6 to 20 micromolar ADP, according to Kent Salin's work and these other people. So we throw in a low amount, and then we just do a super maximal assay. Now, in both cases, whether it's quad or diaphragm, we verified there's a problem making ATP using oxygen consumptions in the mix, okay? Now, ROS production. Most people will just, including us, the standard approach was to just add substrates that generate ROS. I won't get into what that is, okay? You're basically cramming electrons in the electron transport chain. But if you have ADP present, you can change the kinetics. I didn't show you data here in the absence of ADP, but when we did, in absence of ADP, we didn't always see elevated ROS. But as soon as you throw ADP in, you're looking at the ability of ADP to actually lower ROS. The faster you make ATP, common misperception is you make more ROS. You're actually lowering. If you do a ROS assay and you minimize fibers, if you do that, and you add titrate ADP, you actually lower ROS. So what we found was ROS production was in fact higher in these mice with Duchenne if you actually had ADP present, which is more physiologically relevant. Most people that doesn't matter when his ROS is up. For the mitochondria people here, you had to have ADP present, physiological parameter, to finally find yes, mitochondria source of ROS. And we saw that in quad and diaphragm. So this pathway now seemed to be relevant. Elevated HO2 and a muscle weakness, but now we needed a measure of cell death. So apoptosis triggered by mitochondria is typically through caspase 93. It's just a cell death pathway. Now, this often happens in response to calcium stress. You know, I'm getting a little bioenergetic here, but mitochondria can trigger cell death when they get too much calcium. Well, this is a disease of too much calcium. So we did a mitochondrial calcium stress test. You can actually titrate calcium and through various assays, indirectly look at how mitochondria become engorged in calcium, get so stressed, they actually open up and release pro-apoptotic factors. It's called a calcium retention capacity assay. If it's up, it's interpreted as you've got a really high retention capacity. If it's down, it doesn't take much calcium to stress out a mitochondria and make it kill the cell. Diaphragm actually didn't see decrease, but quadriceps did. Okay, well this is consistent. You've got a mitodysfunction, you've got muscle weakness, and the mitochondria are more likely to trigger cell death in response to calcium, and caspase activities were actually trending higher. Why we didn't see the diaphragm, we don't know. So some of the problems are a little more complex. Mitochondria killing muscle cell might depend on the type of muscle, but at least you got mitochondrial dysfunction in both muscles. We then went to histology and looked at necrosis. Visualize dying tissue. It's called an H&E stain. Now, what you're looking at, so the light pink is all protein, and the dark pink is actually nuclei. And this is a healthy, well-type muscle. And I'm sorry it's a little small here, but you can see the outline of the muscle, and you can see some nuclei. Okay? But a dying tissue tends to show up with more nuclei. Does anyone know why? It's immune cells. It's the immune cells infiltrating, trying to deal with this dying tissue. So when you see tons of nuclei, it's actually interpreted as necrosis. Through the roof in the diaphragm and quad. We published that study this year, but we then published another study where the same things are happening in the heart. In fact, the previous data I showed you, the mitochondrial dysfunction occurred at the same time as muscle weakness. This was 4 weeks of age, by the way. At 4 weeks of age in heart, we saw the mitodysfunction but did not see cardiac dysfunction. But we know from the literature, cardiac dysfunction takes a lot longer. So mitochondrial dysfunction in the heart is preceding cardiac dysfunction, which actually implicates an early role for it. So between these studies, we started to lay the foundational work of just laying the map. This is all descriptive work right now, showing yes, mitochondria, ATP production is impaired, fitting with some previous lit. But mitochondria are in fact a source of this. We resolved the problem in literature by thinking about our protocols. This was all the work required to ask the most important question. Should we target it? Should we? We just found associations. Is this really possible? So step 2 for Megan's thesis was to target the mitodysfunction. Is there a drug that will bring ATP production up, ROS down, and will that improve all these muscle force measures I showed you? So we partnered with therapeutics. They're outside of Boston. And they were very great company to work with, super enthusiastic. They all have their PhDs, and they say, remember what it's like to be a grad student. We invited Meg down. Meg is a PhD student. We presented her work. And they actually talked to her about, what's your career plans, and they gave her advice. Awesome group of people. They gave us SPT 20. We were talking earlier, Adam and I, and certainly Dan, this used to be called SS20. For most people, that doesn't mean anything. But what's great is it's pretty non-toxic. It's actually a peptide. And this drug and a more potent variant that we couldn't get our hands on, which is called SS31, have made it to, certainly SS31 has made it to clinical trials. In Huntington's, very rare mitochondrial disorders, trying to improve people's mobility. And it's non-toxic. At very high doses, it's injected. Very high doses, you get a bit of itching. That's it. This is awesome. Can't eat it, because what is your stomach getting peptides? Stomach acid. So other disorders, they have shown you're not going to be a super athlete on this drug. It will not take a healthy mitochondria to make it better. It's a functional shield. It prevents declines in respiration. It prevents elevations of loss. It's thought, but by no means established, that it does so by binding to what's called cardiolipin. Cardiolipin is in the inner membrane of the mitochondria, and it's thought to actually be sort of the anchor by which many of these electron transport chains bind to and stabilize. Like, this is all functionally organized. You do not want these things out of place. They're all tethered and bored in. One of the anchor points is cardiolipin. Big one being cytochrome C. Another thing complex medicine. We have no idea if cardiolipin is a problem in muscular dystrophy. We did find a paper where it was down, but we don't know. We didn't have a cardiolipin basis to test this drug, but we had a functional basis to test it. So what the heck? Let's try it. Yes, currently phase for Huntington's. So what we did was we injected this in the mice, 5 milligram per kilogram standard dose. But the data you saw was so severe, right? A lot of fibrosis, a lot of necrosis. They were only 4 weeks old. That's around the time of weaning, when they get off their mother's breast milk and start eating their own. We were actually worried that's too late. Maybe it wouldn't have been, but we were in this disease is too far gone. So we started at 4 days of age. Tiny little pups. You can actually pick them up like a kitten at the back with a very small syringe, just in the scruff right here, just a little drop, rub it in. Totally safe. We did that for 4 weeks. So we're trying to get this as early as possible. The only thing we could have done earlier was in utero. So here's the data. Gray is the wild type. Blue is the mice with dystrophin mutation. They got a saline in control. We still injected them in case it's stressful. And then here's the drug. Body weight didn't change. And that's not lean weight, that's just whole body weight. But limb muscle volume actually went up, which we reconstructed from the three-dimensional image. What was strange, though, was the volume didn't go down in muscles. This model might have some compensatory regeneration going on even at this age. But for whatever reason, it was still increasing. But we're not going to get too excited again. This is how you do grip strength. If you ever lift a suitcase, or seen the digital meters with a hook, you can lift suitcase, tells you how much it weighs. You can buy those things that read to the 0.01 newtons. And you just hook a little grid on. And anyone know what happens when you lift a mouse up by the tail? It gets in the air. So you just hold the grid and gentle, 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 gentle until they voluntarily release. Do that a few times, take the highest reading. Massive impairment, but look at the drug effect. Dollar sign is greater than saline, but not different. It was not statistically different than the wild type. So that right away was interesting. K-chain time, you actually take the cage lid on the bars, put the mouse on top, put a pillow here, you go whoop, and get your stopwatch up, and they hang on. Didn't see an effect. Distance run, voluntary wheel running, didn't see an effect. What is the problem with all of the assays I've shown you so far if you want to know if muscle function improved? There's a couple of problems. First of all, they're not necessarily isolating just muscle function. Second of all, these are all voluntary. They still choose when to let go of the grip. They choose when to fall. How do you think you feel if all your muscles are being torn apart? In pain. We're assuming the muscles still feel terrible. Targeting mitochondria does not destabilize the cell membrane at all. In fact, when you lift the lid, they're still in the corner like this. These are voluntary tests. You got encouraged by this. So now you need to remove the voluntary factor. You need to isolate the muscle function. So now we stimulated force production. This one we took out of, no, this was in vivo. This was in vivo. Instead of going Hyman, we now went to the quadricep muscle. There's assay reasons we did that. And we stimulated force production, direct stimulated, very anesthetized, no voluntary control. Pain and how they feel, not a factor. And we did it with the diaphragm ex vivo in strip. The quadricep data, we stimulate at various frequencies. Force goes up in a wild type. The blue is the Duchenne. The green is the drug. And there's no statistical difference between these two. These symbols here are saying that both B and D groups are different than the wild type. Then we went to the diaphragm. Here's your wild type force. Here's the dystrophin mutant. The green line is the diaphragm. Dollar sign is drug difference sailing. We had a main effect where there was a partial restoration of force, about 30%. So that was provocative, because that is the cause of death in 40% of patients. We then went to histology. Remember, as your muscles dies, it's replaced with fat and scar tissue. In fact, the diaphragm, several years in, is almost all collagen. Only a few fibers left. It's amazing you're even quicker. So you can stain collagen. Collagen shows up as red. All fibers have collagen on the outside. It's the extracellular matrix. But here is the Duchenne mouse. Tons of collagen, which are the scar tissue. The drug actually brought it back down in the quadricep. Well, that's weird, because if I go back a slide, I didn't get any force benefits. Okay, so I've got less scar tissue, that's great, but I didn't get force improvement. The diaphragm, no effect on fibrosis. But that's weird, because back here I got the force improvement. We don't know the answer. I do have a theory. I haven't got to the mitochondrial data yet. The drug improved that. Diaphragm are highly oxidative. They're highly reliant on your mitochondria as a source of energy. Quadriceps, a lot of type 2 fibers. Probably less reliant on it. Bigger impact for function. Fibrosis is much harder to explain how mitochondria lead to fibrosis than we go through dying cells. We've got to figure it out. Here's the data. In quadricep and diaphragm, we've got the dollar signs on oxygen consumption. So at any ADP we use, a physiological, a high one, or a saturated one for concentration, we've got the same story here. Wild type, the dystrophin mutant was down, a very subtle restoration of respiration. Very subtle. Same in diaphragm, dollar sign. We look at the Ross, wild type, Ross was up, and the drug was bringing Ross back down across a range of ADPs in both muscles. We got the dollar sign. So that first study that laid out the foundation, low respiration and high Ross, we targeted with a compound that in other diseases is known to correct those. We did correct it with Duchenne as well, in the mice with dystrophy. But that functional data was very bizarre. That improvement in mitochondrial function translated to improved force in diaphragm. I buy that. It's more oxidative muscle. The fibrosis, we can't explain. But at least it's beneficial for quadricep. We also looked at other markers of mitochondria. We looked at ultrastructure. Dark blotches here are mitochondria in a healthy muscle. And in Duchenne, you see less blotches. You get less mitochondria. So mitochondrial size was down. Mitochondria per unit area, or as a percent density, it's the same thing, it's down. But look at this, the drug brought it back. So the drug actually, not quite in the, it was intramyofibrillar mitochondria and subcircular. Got mitochondria deep in the muscle and then some under the cell membrane, subcircular number. So you can count the number on your cell membrane, put it in your SS, count the number deep, the IMF. Got a lot of dollar signs, not everywhere. But we didn't just improve function, we improved content. So maybe that's part of what's driving this. Diaphragm, a little bit, but not much. So what we learned is there is a mitodysfunction. If you correct it, you get divergent benefits. You either get a force improvement or you get less fibrosis. Now those are only two muscles. what we've learned from that heterogeneity is you cannot make one conclusion for a whole body benefit just based on two, although at least we did two, diaphragm and quad. But it is showing some benefit. So we tested another drug, alessazine. This is actually the only commercially available mitochondrial-targeting compound I've ever found. You can buy it from Tokers Bioscience, which is crazy because Roche actually has the patent. And I spoke with Roche and they actually had no idea how to buy it commercially. They didn't know this because I don't know how that happened. This thing's awesome. Now it's a cholesterol-like structure. Party line is it binds a channel on the outer mitochondrial membrane called VDAC. It's a very important protein. It does a lot of things. It forms part of the cell death signaling cascade, causing through a permeability transition pore. What that means, it's involved in energy. It's how ATP leaves a mitochondria through this pore. Okay, and it also regulates membrane potential somewhat, and therefore regulates ROS. All we know is this drug binds it. In models of ALS, a disease of neurodegeneration, in the rodent model, cell culture model, you put lecithin in the rodent or in the cell culture, you get less neurodegeneration. It stops neurons from dying. And some mass spec data showed up on VDAC, and they just thought that's how it works. But it prevented decreases in respiration and elevations in ROS. So again, we used a functional rationale to test it. Now it went all the way to phase 2 clinical trials in another muscular dystrophy called spinal muscle atrophy, a disease where the spinal muscles atrophy and you have a tough time walking. And at 12 months, it was actually improving. Anyone heard of the 6-minute walk test? A lot of mobility people here. It improved the 6-minute walk test. How far can you walk in 6 minutes? It's not far. That's a clinical benchmark to improve their therapies. So when we saw that, when we saw the cell culture data where it was rescuing mitofunction in disease models of various things, we go, let's try it. So Catherine has taken this up. Took the same mice, we started a little later at 10 days of age for various reasons. Awesome, we don't have to inject, you actually dissolve it in vegetable oil, hold a little drop, mice eat it up. Don't even have to gavage it, eat it all. Control, just vegetable oil. She just finished the wild type group, so I don't have that data. I've just got drug versus vehicle. Body weight didn't change, but the weight of the quadricep increased. It's a muscle wasting disease. We just slowed it down. We're actually looking at the wild type now to see how much it can do. So then she measured torque in the quadricep. This is the max force, okay? Now, what's interesting is we did a different assay. We're learning as we go. You do your torque frequency curve, muscle gets, you fatigue the muscle, and then you wait, you do a 5-minute wait, 10-minute wait, 15-minute wait to stim it again and see how much they've recovered. So imagine doing do a bunch of exercise, wait 5 minutes and sprint again. What percentage speed did you have at first? This is recovery from fatigue. The drug is accelerating recovery from fatigue. It's another way to measure muscle weakness. So we got bigger muscle, we got the accelerated recovery. Cage hang time improved. So what we looked at this relationship again, at mitochondrial function and all of these indices. When we looked at the calcium retention capacity, this index of how a mitochondria kills a cell, we actually saw no effect. When we looked at H2O2 emission, we had a surprising decrease. Sorry, not surprising. We had a surprisingly non-significant decrease. We had a large N, but we went back and in the vehicle control group, we had a lot of variability. So we're actually bumping up the N and brain power. And respiration was rescued at a physiological rate. So we got the bigger muscle, we got the better recovery fatigue, and we corrected some dysfunction partially. We're going to see relative to wild type how good that was. So between these two mitochondrial targeted compounds, where the mechanisms aren't fully worked out, they both did the same thing. They both rescued some aspect of mitochondrial function, and they both rescued some aspect of weakness. The divergence across muscles is really strange. The lecithin I only showed you the quad. She's analyzing the diaphragm now. The heterogeneity we saw with the first drug, we're going to know if we see the heterogeneity the same in a second. But what we've established is in a mouse model of this disease, correcting the mitodysfunction does provide some benefit to us. In the disease, where all we're doing right now is targeting inflammation. That is not the cause. It's not the cause, but it's a contributor. What if mitochondria are a second thing we can target? Both of these compounds have not been in trials. Fortunately, we just learned a few months ago that Roche pulled the trials on molluscum because they went to 18 months instead of 12, and it wasn't really working. But that's in spinal muscular atrophy. Duchenne is different. We take these questions and we apply it to chemotherapy. Why do chemotherapy is muscles move? Doing the same thing. What's the relationship? We went out of our comfort zone and actually did the opposite. We tried to make a mitochondrial necrosis by turning on fat oxidation and kill colon cancer. But we didn't do it with breast cancer, heterogeneity across cancers. We're asking the same question on fill in the blank. And you choose your fill in the blank. Our new direction is based off this great study gained in Arkansas, where he found in a tumor-bearing mouse, the muscles waste away by 4 weeks. But at 2 weeks, you saw the mitodysfunction in the muscle. Mitodysfunction precedes cancer cachexia. So Luca is in the master's student lab. Guess what he's doing? With tumor-bearing mice now, which we just set it up this month, got the data, we got the atrophy in the model. He's giving molluscum. So we're going to see the same question, targeting mitochondria can slow muscle wasting in cancer. It's all the same question. It's all the same question. Because there is evidence to suggestive associations, now we go after the causations. And we've been really fortunate to collaborate with Thomas Hoflab at Masters, who's a joint senior author and joint first author in May, to just characterize diseases that people never thought there was a muscle dysfunction, type 1 diabetes. We saw, this is just calcium retention capacity, but we saw problems with respiration loss as well. And it's crazy because these people, based on self-reported questionnaires, you know how much exercise they were getting each week? They were 23 to 25 years old and were all lean. They had over 200 minutes of exercise. That's exceeding national guidelines for physical activity. Mitochondria were swollen. Mitochondria were sensitive to calcium, which triggers cell death in the modeling. Other graphs show loss was up, but lean and they're active. So why would type 1 ever do this? So if you identify as a student what your expertise is conceptually, think outside the box, all the things you can apply to it, you start making really crazy discoveries. And for any mitochondria guy, and we've got several great faculty here doing it, think about not just doing the protocol everyone does. Think about, what am I asking? How are mitochondria regulated? And does my question maybe allow me to add more things to the buffer that capture a relevant pathway that was relevant to my question? Because when you do, you can get a totally different conclusion that takes you down a new path. And we do this not just in diseases in mice. We ask the same sort of, there's a lot of words. We modeled other stuff in humans with exercise. We published a paper, others have done this too, where they actually started adding other things to their buffer and just took a biopsy before an exercise. How's exercise regulated mitochondria? Okay, pre-biopsy, post-biopsy, but we changed our buffer and we got a totally different conclusion. Try to model the in vivo all the time. Megan and Sophia worked together. Megan was Duchenne, Sophia was chemo, was help each other, just outstanding enthusiasm. If I keep talking, I'll get a little teary. Proud of them all. Catherine is coming, all done well with Les is active in cancer. Luke is doing the tumor model. All of these students. Payman is an incredible undergrad student. He figured out how to use this huge CT scanner for mice as an undergrad student. And then he left the lab and gave us, without me asking, a manual for the next CT. I've just been so fortunate to work with them. And that's what I mean. Have fun with what you do, right? But at the end of the day, it's this. Especially these people. Sorry I went over. Thank you.
Okay, a couple of minutes. Questions for Chris?
This is just a do you have a hunch kind of question.
Yeah.
I know it's not really what you asked, but I'm always intrigued about dystrophin in the brain. They don't really know what the heck it does, and there's this cognitive decline in the DMD boys, and some anecdotal evidence that you and I were talking earlier about NERV2 and oxidative stress. And as you know, parents of DMD boys will try anything. And so they set out to see if they had any muscle strength changes with these NERV2 activators, and the moms all said no. And this is all independently of one another. They all said their cognitive function is better.
No way.
They pay attention. They can follow a chain of tasks that I tell them to do. So all anecdotal evidence that what's your hunch on mitochondria as a secondary contributor to a cognitive decline in the brain.
We've got this great lab at York, Dorota Crawford's lab. She has a mouse model of autism. And so she does all these behavioral tests. And I said before we even started, a few days before we do our tests, can your students come in and do some behavioral, because the brain is the next most abundant source of dystrophin. Not all cells express dystrophin. If you go to Human Protein Atlas, you can look at all organs that express a gene, muscle and brain, just as you said. So when I saw that, I was right on what you're saying. And the problem was the mice have to be in the environment for weeks to become accustomed. And we're only given for 4 weeks. So my hunch was obviously that we're meeting some sort of learning problem, because the brain also lacks dystrophin. I have no idea if the brain mitochondria dysfunction. But why wouldn't we, after what we just saw? We're this close to doing it, but it would actually require a whole separate release. The answer is my hunch is yes, and I could get some more money.
These mice have a decline in something.
You know, there's very few papers on the D2 model, because it's a relatively new one. I've not seen any behavioral data. To be honest, I haven't looked. But in this classic mouse model, there's behavioral data stuff. I haven't been able to reconcile how much of that is just in pain and choose to stay behind. There's so much behavioral stuff that's movement-based. So I don't really know if it's a model. Yeah.
Beautiful talk. That's, a couple of things I know I can't time to ask, but I'll do one comment and then a follow-up question. Regarding the fibrosis resolution with the SET20.
Yep.
Right? But not an improvement in strength. Mitochondria, as you described so well, both play a role in supplying energy, but also determining cell fate.
Yep.
Could you just be preserving muscle mass, right? So the cells survive because the mitochondria are killing them now, but you haven't resolved the dystrophin defect, right? I mean, there's no way that's going to reconnect, right? So the cells aren't going to be stronger, but they're just going to still be there,
right?
Because the mitochondria are perhaps those other things that are killing them.
Yeah, are we just keeping cells around longer?
Yeah, and of course, if you regularly repair in this model, it's trying to help itself right now. That then explain why the mass is greater, because that it's able to actually manifest now because the mitochondria are, chopping the legs out of the effort.
So particularly where there was less fibrosis,
right?
The quadricep.
Right. Yeah, because fibrosis replaces dead cells, so that's what I think.
So in the quad, do we have less fibrosis because we're keeping the cells around longer? Right. That's a great question. One of the next studies we need to do is look at the role of mitochondria in stem cells. First of all, are they dysfunctional? Are you weak because you can't regenerate because your stem cell mitochondria are weak? And could the drug have rescued, the force of action? Because I'm actually boosting mitochondria in the stem cells and now overcoming what I am predicting is a metabolic insufficiency for differentiation. That's one of the next studies we're going to do. But that's a force-linked question. What you're proposing is a fibrosis-linked question to cell rescue. That's an interesting idea. I had not thought of that.
The follow-up question is, what about endurance, right? So if you get like a walk kind of with mice, I know that can't really run.
Force treadmill.
Yeah, right. Some kind of endurance.
Yep. The original study design on the blackboard had endurance stress test. Now this runs into a bit of a problem because these membranes are weak. So if I exercise them and then 2 days later do my muscle harvest or mitofunction, have I ripped them? Now Mark Tanopolsky published in the classic model that light to moderate intensity exercise doesn't rip the membrane. You got to go to high intensity. So we're like, well, okay, we'll do a light intensity, moderate intensity protocol and see how long they go. And then I'm like, yeah, but what are we doing with the mitochondrial function? That needs a separate group of 12 mice. We read these. I think both of the studies you saw cost a little over 10,000 animal facility charges. So I had to cut it off. Guess what? How many of these answers are in the grant teams? All of them. I saw hands over here.
All right, one more question.
Student. Oh.
I'm wondering, do you know how much is known about the direct contribution of mitochondria dysfunction to inflammation as observed in DMD? So maybe like the inflammasome or something would be an obvious translator of that. And so like if you were to combine anti-inflammatory treatment with one of these mitochondrial therapies, would you get additive benefit, no additional benefit?
Yep, absolutely. And another part of the aim was driven more top-down view at combining the two drugs, clinical relevance. You know, if this is ever going to make it to a clinical trial, you know, it's never going to substitute existing therapy. It's got to be an add-on. And certainly, it's a positive control experiment. You know, here's what we know works in muscular dystrophy: prednisone, glucocorticoid. So that's been positive control to compare this drug to, but also clinically relevant. An add-on, a combined group. And I view that from a clinical perspective, but from a cell pathophysiology perspective, that gets a little more complicated. How do mitochondria trigger inflammation? Well, I can certainly see that indirectly by just causing the cell death to begin with. And as soon as any cell dies, how does it recruit an inflammatory response? The damage associated with molecular pattern. Releases intracellular factors that should never be outside. And the immune system recognizes that. That's why if you cut yourself, you're red within seconds. Damaged cells released all these damage associated with molecular patterns. The immune cells come in and you flare up. That's indirect. If a mitochondria has killed a cell, well, then you get a damage response. But a direct signal, there are theories out there, but I don't understand how that happens, to be honest. It requires some retrograde signaling in the absence of cell death. So I don't know about that. We are proceeding with what makes sense to us, which is a cell death mediated inflammation. So that's an I don't know. Yeah.
Okay, so thank you, Chris. We have a little gift for you.
Oh boy!
And if we can just
More water?
one more time. Thank you, Chris for coming.
Thanks very much to everyone. I'm sorry this is after the board. Thank you.
And if you guys have more questions for Chris after recitation, he'll be at row 34 for a little while. So.
I keep hearing names of restaurants that sound like things that aren't restaurants. And I'm assuming that's a restaurant. So.